Hi, I am Suraj, a PhD scholar in the Department of Mechanical Engineering at IIT Kanpur, India. So today I am presenting my paper, that is development of a smart FBG-based surface roughness measurement system for real-time evaluation. So surface roughness plays an important role to determining the performance of the mechanical component by influencing the factors such as fit, friction, precision, or stress concentration, etc. So there are two types of surface roughness measurement technique. First is the contact methods and another is non-contact methods. So contact methods, when in contact methods, the stylus will physically touch the workpiece surface. So during the measurement, so the soft surface may be damaged by this method. So this type of surface is not suitable to measure the surface roughness by this process. So non-contact method is used to measure the surface roughness of material without touching the workpiece surface. And this method can measure the surface roughness up to angstrom. But the surface like dark material or transparent surface is not suitable by this methods, because this method is used optical lights. So both of these methods, the instruments which used is bulky. So the complex surfaces the surface roughness of complex surfaces is not measured. It is measured only simple surface. So to measure to predict the surface roughness of complex surfaces, the researchers introduce the machine learning to measure the surface roughness of the uh, to predict the surface roughness of the part during the process by analyzing the process parameters of the manufacturing process. So this technique is useful for very specific process and material used, and they lack the flexibility to generalize across various surface types of machining condition. So our paper objective is to develop an FBG-based surface roughness measurement system which can predict the surface roughness of more than 500 nanometer, even for complex surfaces. So for this, we have used FBG sensor. So FBG sensor is the periodic modulation of an optical fiber core reflective index, in which the broadband band light will passing through the fiber, then most of the light will be refract through this, and some specific wavelength of the light will reflect back. And this wavelength is called Bragg wavelength. So the magnitude of the Bragg wavelength is depending on the external factors such as stretching, compression, or environmental temperature of this fiber. The mathematical equation for Bragg wavelength is given in equation number 1. So to development of FBG-based sensing system, FBG is placed into the silicon-based compressive agent, which is the silicogest. And one end of this silicogest is uh, stylus is attached, and this stylus has moved in X and Y direction with the help of linear actuators. When if, when this stylus will dragged onto the surface, the FBG will experience the uh, compressive strain. Then the FBG interrogator will record this Bragg wavelength change due to the compression of this FBG, and save this Bragg wavelength data in this system, in this computer. So an AIML regression model has developed to take this uh, Bragg wavelength data and extract the statistical wavelength features, and map these statistical wavelength features to actual surface roughness obtained from the optical profilometer. So this is the experimental setup of this FBG-based sensing system, in which the FBG is used of central wavelength of 1552 nanometer, and bandwidth is less than 0.5 nanometer, and reflectivity is more than 90%. A silicon-based compressive medium is used, which is silicogest. The compressive properties of this silicogest is shown in this figure. And diamond tip stylus is used of 2 micron radius tip is used with linear actuators to move the X and Y directions to drag the surface. A smart scan uh, intro a dynamic FBG interrogator is used with its software to record the data from the FBG and save this data in this computer. In this this is the workpiece, which is a flat sheet. So at this time, the workpiece is the flat sheet, but we can use the complex surfaces. And when we will use the complex surfaces, the movement of this stylus will change according to the surface, according to the geometry surface of the workpiece. So after the development of FBG sensing system, the regression model has been developed, and this model have taken the Bragg wavelength data from the uh, saved saved in the computer system, and can extract the statistical feature, that is mean, standard deviation, standard error, mean absolute deviation, first, second, and third quartile, and map these statistical features with the actual surface roughness obtained from the optical profilometers. So to training this machine learning regression model, 36 workpieces have taken, in which 24 workpieces of mild steel and 12 workpieces stainless steel. So when mapping these statistical feature, that is mean, standard deviation, standard error, mean absolute deviation, first, second, and third quartile, with actual surface roughness of the obtained from the optical profilometer, we saw that the uh, mean mean wavelength feature gives the accurate result as compared to the other wavelength features. As shown in figure this, in which the this is the mean wavelength features versus surface roughness, and with the combination of X and Y data, that is in 3D, and this is the separately X direction, and this is the separately Y directions. We also saw that when we use separately, that means in 2D, then a parabolic curve is obtained, and when we used in 3D, then it is approx linear graph. It is because the optical profilometer gives the surface roughness in 3D. So after the validation, after the training of this machine learning regression model, uh, 5 another different surface roughness workpieces are used to validate that machine learning regression model. And when we uh, we predict the surface roughness of these 5 another surfaces, then we saw that the wavelength features, that means being a standard deviation, standard error, first, second, and third quartile, we saw that the minimum error is the 5.26 nanometer when we use mean wavelength features. That means the mean wavelength feature gives the accurate results as compared to the other wavelength features. So this is the conclusion of my work. A smart FBG-based sensing system for measurement of surface roughness is developed to measure the surface roughness of real time, even for complex surface also. This system is used an FBG-based sensor system, which gives the wavelength shift data, which is fed into the machine learning regression model, that analyzes the statistical features and predict the surface roughness of the which surface which have greater than 500 nanometers of density. This machine learning has been trained using 2D and 3D wavelength shift data from the FBG system against the surface roughnesses of obtained from the optical profilometer. This system is used to predict the surface roughness of different workpieces and so that the mean wavelength in 3D gives accurate result with the average error of 0.005 micrometer, that is 5 nanometers. Thank you.